Okay, let's take a look at question 15 and topic set 5. This question tells us that we have an ideal gas sample at a certain temperature and pressure and volume, and then it's composed of 50% helium and 50% xenon by mass. And the question is, what are the partial pressures of the individual gases? Okay, so in terms of partial pressures, you want to think back about our discussion about Dalton's Law. You have both helium and xenon. You can calculate the pressure two different ways. One way to calculate partial pressure is you use the ideal gas equation. Pressure of helium, for example, could be calculated as nRT over V, where N here is the N of helium, the number of moles of helium. Now, the other way to calculate partial pressure is you can also use the mole fraction equation, which is mole fraction of helium times the total pressure, okay? And mole fraction is the fraction of the gas that's just the helium. So in other words, you calculate it by taking number of moles of helium divided by the total number of moles, which is helium plus xenon, and times the total pressure. So notice that in either way, you're going to have to get this value of number of moles of helium. But the problem with this approach right here is, and so a lot of times what people say is that, well, let's just assume that we have 100 grams of the gas, right? Because it says that we have 50% by mass of xenon and 50% by helium. So let's say you do that approach. So if you assume 100 grams of gas, then of course that would mean that 50 grams is helium and 50 grams is xenon. Now from here you can then calculate the number of moles of helium by taking 50 grams divided by the molar mass of helium, which is 4. The problem with this approach is that if I were to assume a different quantity of gas, 10 grams of gas instead, now instead of 50 and 50 I have 5 and 5, and that means the number of moles would be 5 grams over the molar mass, which is a different number. It's actually, as you can see, 10 times smaller than the previous assumption that I have, right? So the number of moles will not be the same in these two assumptions. And if the number of moles is not the same, that means that if you plug it into this equation right here, you're going to get partial pressure values that are going to change based on your assumption, okay? And obviously, the answer cannot change regardless of the assumption you use. You have to have the same answer for this question. So as a result, this approach will not work to solve this problem. We don't use this here because the answer will change when the assumption is changed. Okay? So the best way to solve this problem is, instead of using some type of number to assume, we would just use a variable. We're going to assume a total mass equals to x. That means that the mass of helium is going to be 50% times x, or half x, and the mass of xenon is also going to be half x. Okay. And then what we'll do is we'll use this to convert to number of moles, and then we'll use the mole fraction concept to help us calculate the pressure. And you see that when we approach it that way, it doesn't really matter what the x is. It would eventually cancel out because we have a ratio expression right here, right? Ratio of one number to another. Okay, so let's think about what the number of moles would be. So the number of moles of helium would then be half x over 4, and then of xenon is going to be half x over 131, which is the molar mass of xenon, okay? And remember, what we said is that we can calculate the pressure of helium if we take the mole fraction of helium times the total pressure. So let's do that. Mole fraction of helium is the number of moles of helium over number of moles of helium plus number of moles of xenon. Number of moles of helium, we just said, is half of x over 4. Number of moles of helium at the bottom is half x over 4, plus number of moles of xenon is half x over 131. See, what I can do here is factor out the half x. So I have 1/4 on the top, and then if I factor out half x, I have 1/4 plus 1 over 131. And of course, the half x cancels out, so you can see that whatever I put in as x really doesn't matter because it will cancel away, and I just have a ratio of numbers which I can calculate. And I end up getting 0.970 for the mole fraction of helium. Partial pressure of helium would just be 0.97 times the total pressure, which is 600 torr, and that gives me 582 torr. Then for xenon, be 600 minus 582, giving me 18 torr. So again, the lesson of this question is that you want to be careful which approach you use to calculate the partial pressure, because the first approach would not be right. So in this case, you have to use that approach in order to get your partial pressure.